Well, hi everyone. I can't see anything. So you know, I know that it's 20 past 5 there, and I'm the last obstacle between you and beer. So I can assure you that I can't see a thing. So if you really want to just file off and you know, start having beer now, that's okay with me. As long as Ken tells me at the end it was a massive audience and they were really thrilled with my talk. So what I want to talk today, and I'm really sorry that I couldn't be there in person, is about I guess trying to maximize value from geophysical surveys. I'm just trying to get my thing up so that it doesn't have a bunch of other things in the way. I don't know if you guys can see those various things, but anyway, I'll keep them in the corner. So there's a very long list of authors here. Pete Betts is listed as the first one. I think he's been the most active in this area for the longest. I was kind of there to start with him, but diverted into other things. But then there's a long list of blue and purple people there. The blue people are all Monash people. I could be both colors because I started at Monash and now I'm at U. And the purple ones are the UQ people. And really, both of these groups are very focused on trying to do really value-added geoscientific studies of geophysical data in geophysically-driven exploration settings, and that's really what I want to talk about today. Okay, there we go. And I'm sure this won't be the first time you've heard this issue or discussed this today, but really the big issue is that certainly in Australia and in a lot of other jurisdictions, the major mineral deposits that have been discovered have been mostly outcropping, and we have not been very good at exploring undercover. There's been limited success at depths of greater than 50 meters, and lots of people, including I think Richard Jolly, who presented today, have pointed out that as you go to these deeper levels, the importance of geoscientific understanding becomes greater and greater because the number of direct detection tools you have become less and less. And there's a whole bunch of different aspects to that, but I'm not going to talk about those. I'm really going to focus in on what we can do to add to that geoscientific understanding undercover. And the two, I hope you can see my mouse move around here, the two different areas that we're going to talk about are, first of all, the Mount Woods area, which is host to the prominent hill deposit. And if you look on this, I'm on the color magnetic image down here. So if you look at where my mouse is there, that's where the Mount Woods area is. I'm going to start on that one, and that's a set of slides mainly generated by Pete Betts, but it's work that I've been involved in and co-published with him on. And then I'm going to talk about some work that we've done more recently in the eastern succession of the Mount Isa and Lyre, and also talk about some of the exploration history in that context. So the reason I put this slide up is that this is a selection of slides taken from a 2019 talk that Pete gave at the AEGC in Adelaide. And again, I'm not going to go through all those authors. Suffice it to say that there's a large group of people involved there. So now where we're focusing in again, so we're in an area that's off to the northwest of Olympic Dam in the Paleo Mesoproterozoic Gawler Craton. And what I want to do now is just show a few slides to go through the history of the evolution of the interpretation in that area. And I should point out as well that this work, this work began in various little stages of it. Began about 30 years ago when I was just a budding young academic. Pete Betts was an honors student. And we were doing work in the Mount Woods in Lyre actually with BHP. So some of the other cast of characters involved at this stage were Tom Whiting, Ken Witherly, who seemed impossibly old to me at the time, but I suspect was probably in his 30s, and also a number of other people, Tracy Kerr and some other names that people might know. But what I want to say is that at this stage, this is kind of representative of what I think a lot of people imagine regional interpretation studies to be. We were dealing with 400 meter space data, so 100 meter grid, which by today's standard would be taken to be pretty regional data. We did some basic interpretation and forward modeling of the magnetic data, and we actually did some field visits and no geochronology, but some structural measurements, some rock property measurements, and you can see in that in the bottom middle here an example of the sort of interpretation product that I'm sure a lot of you have seen that would be considered to be an interpretation map that might be produced from a geophysical interpretation exercise. So we looked at the area, and then you could see a number of folded magnetic units in the region. So we said, oh, well, folding, that's a compressional regime, and we could see a bunch of faults that were truncating some of the folds, and so came up with a history, but those faults that were truncating the folds were interpreted thrust. So it was all interpreted in the context of a compressional regime, and then we did some rudimentary forward modeling, just really testing interpretations to see if they could be made consistent with the gravity and magnetic data. And one of the challenges that you see in the Mountain Woods area, of course, is that the outcrop is extremely sparse. And even where it's exposed, it's very poor. And then the final aspect is where it is exposed, and you can see this down in this picture right here, it's very, very complex. So we're not dealing with something where you've got very simple rocks. We've got high-grade, wholly deformed, metamorphic rocks with very little geochronology, and so it made it a very challenging area to carry out an interpretation. Oops, go backwards here. The reason that this got put up is that I think all of us are increasingly of the view that there are a number of steps that you need to do to get past what I just showed as an early rudimentary interpretation. And one of the things that you need is a time-space map of this type that's usually based on a geochronological background, regional analysis of different rock types, and a consideration of their relationships to each other. So when you start pulling apart this part of the world, so we're going to older rocks at the top of the screen and younger rocks at the bottom of the screen, what we see is that there's a youngest Archean, oldest Proterozoic sequence called the Malgathic basement complex, and then there's a number of metasedimentary complexes that are sort of the 1900 to mid-1800s range. Then a strong orogeny, the Hinman orogeny in this part of the world. There are other synchronous ones elsewhere in Australia that are deforming those rocks. And then, as we see all over the Gullah Craton, the Stewart Shelf, a big outpouring of volcanics and intrusives around that 1600 age that correlates in time with Prominent Hill, with Carapatina, and of course with Olympic Dam. So, and I guess the point, I don't want to go into any more detail on that here, but the point is to say, if you don't have one of these when you're carrying out a regional geophysical interpretation, then you're probably not going to arrive at a geological map. You're going to arrive at something that shows magnetically, magnetic units and some of the structures, but doesn't really turn it into a geological understanding. And of course, what we're showing here is that as time has evolved through surveys and private exploration, the standard that we come to expect from data gets better and better, and what that means is that we're getting greater and greater information from the surveys. I'm sure that's been covered today, so I won't labor that anymore. The other change that happened here that allowed an evolution of the interpretation, of course, is a much greater geochronological study. So again, I'm not going to go through all these other than to say that all these different colored stars represent different suites of sedimentation, intrusives, and metamorphism that have been able to be elucidated through a more comprehensive geochronology data set that really form a very important input to coming up with a better geological map interpretation than the one I showed at the start of this. And the other thing is, and this is kind of jumping ahead to the interpretation, probably at a stage where I haven't showed enough information to back it up, but I'll go through some of the information in a second. But the other thing that I guess you have to have in mind when you're carrying out this sort of interpretation is what assemblages of structures look like and represent for different tectonic environments. And what I'm going to try to show you now, going through this, is that there are some aspects of this area that, as the geoscientific understanding has evolved, it's become clear that there are aspects of this area that provide support for the interpretation of a metamorphic core bond. First, though, this is the next, I guess, iteration of interpretation, if you want to say that. So, with the higher resolution data, when you compare that to the original interpretation, what we can see is that there's a much more detailed consideration of structure, of both of the distribution of units, of folds, but also shear zones and faults, and a much more comprehensive consideration of the stratigraphic picture and what units correspond to where in the area. So what we have now is an interpretation that looks a lot more like a geological map than the first one. But then there's some interesting things that started to come out of that, and that was that you could see in this area, in this central area of the region, what you can see is that there's an area, all these yellow rocks on this diagram are relatively old rocks, the Mount Woods Metamorphic Complex and associated magnetic units, relatively fewer intrusives, really strong ductile polydeformation. And the other thing that you can see is that ductile polydeformation is strongly truncated by these northeast trending and southeast trending shear zones. So, and we noticed that in the first, in the first interpretation as well, but it's really very much clearer here. Really strong evidence that there's quite an intense period of polydeformation that has predated these northeast and southeast trending shear zones that we had originally interpreted as thrusts. But having done all that work and going back to look at the outcrops now, what you see is that the interpretation, the thrust interpretation, the interpretation of compressional tectonics doesn't really hold up. So with the spatial context that's been provided by the magnetics, you go back to the outcrops. So in this area in here, the moonlight shear zone, when you actually go and look at it on the ground, it's a steep westerly dipping shear zone with sinistral and oblique normal movement. In other words, west side down movement. It's not a thrust, it's a normal fault. And then when you come down to the southern shear zone, it's actually got a moderate southerly dip and again, oblique normal movement. So all of those observations, this observation that the overlying shear zones that are truncating this polydeform basement are normal faults, not reverse faults, contributes to, or I guess supports the idea that maybe we're dealing with a situation where we have a detachment between polydeform ductile lower plate and an upper plate that has more brittle structures, younger rocks, and in this case is intensely intruded by hiltical sweet granitoids. And some examples of that where we're seeing these straighter shear zones of the upper detachment truncating structures in the basement. And then that has allowed the interpretation to go back and place a lot of these structures that were just lines in the previous geophysical interpretation into an interpretation that that fits with the observations that support the idea that this is a core complex where the lower plate is sitting in here, and then we've got a more brittle upper plate sitting on top of it. So I guess the lessons from that sort of interpretation is, you know, and the obvious one that I'm sure you guys are well aware of is that you know, when you've got a 12-meter grid versus a 100-meter grid, you can get you know, a huge amount more structural information out of it, much more sophisticated interpretation. But the other contributors to a better interpretation were better geochronological constraints that allowed a richer mythological interpretation and interpretation of the age of different structures. And also, I guess, all of that contributed to placing the sparse exposures into a context that that allowed interpretation of the kinematics of some of these structures and changing completely you know, the regional interpretation associated with it. And that's when Pete says we got lucky as well. You know, there was every chance that maybe those shear zones wouldn't have been exposed, and then you wouldn't have been able to sort it out. So there's an example from the Mount Woods inlier. Now what I want to do is pass on to the Mount Isa region, because that's an area that we've been working in for the last little while, and Pete has continued to work in. What I'm showing here, though, is a diagram that's actually looking at age of discovery and discovery method, and let's only concentrate on the red dots for this talk, because those are the geophysical discoveries. Of course, the discovery history of the Mount Isa region goes back into the 1800s. I'm only going from the mid-1950s here, showing that the orange and yellow dots are prospecting and geochemical discoveries. So there was a sort of a drip of prospecting and geochemical discoveries until the mid-80s to mid-90s, when we suddenly had this explosion of geophysical discoveries. And you know, Maronin, Eloise, Osborne, Coulthorpe, Ernest Henry, Cannington, you know, mixture of IOCGs and Broken Hill type deposits. And the interesting thing is that after the mid-90s, there were enormous amount of what I'm showing up top there is enormous amount of academic studies of various aspects of these deposits, and these areas thinking, wow, they're really very prospective. We can, if we develop a better understanding of everything, we're just going to blow the lights out in terms of further discoveries. And every discovery since then has been either geochemical or drilling next to where stuff is already. There hasn't really been, with an exception that I'll show you in a second, another geophysical discovery. So just a couple of things I want to comment on that I think are relevant to consideration of the value of regional magnetic surveys. And that is, you know, to say, well, what happened in the mid-80s to mid-90s that suddenly led to this explosion of discoveries? So on the left here, what we're looking at is a picture of the magnetics for the Osborne deposit and the Coulthorpe deposit to the west as well. But you know, it shows why a lot of those deposits were discovered, and that is that in the higher resolution data, but probably even in the older data, there were a series of iron oxide copper gold deposits that were strongly magnetic in this area, and so really once people worked out the self-demagnetization and a few other things, then they were able to drill things like Osborne and put them into production, and there were clear magnetic anomalies. And then on the right-hand side, and this is an image that would be dear to Ken's heart, no doubt, what we're looking at there, that arrow is pointing to the Cannington deposit. On the right-hand side, we're looking at 200-meter space data that was released by the survey, but BHP, when they were exploring in this area, had comparable data in terms of quality. And what you can see is that there's that magnetically dead area, non-magnetic P-lights with iron formations and and magnetite-bearing rocks associated with the Cannington mineralization, producing not a super high, but a very distinctive anomaly that actually coincides with mineralization. And again, when you go back to the regional data, if you look at the lower resolution data here, you can actually see the Cannington deposit in that data, but not very well, not enough. You certainly wouldn't have the courage to drill it, and you probably wouldn't think twice about it in the regional data. So that's one of the reasons. That really summarizes the reason that that all those discoveries were made at that time. It was the step change afforded by this higher resolution. So that was in the mid-90s. 25 years later, we spent the next 25 years drilling more magnetic anomalies and more magnetic anomalies and more subtle magnetic anomalies and other magnetic anomalies, and not finding another equivalent to the quality of deposits that were in those that were in those original discoveries. And this slide really speaks to other approaches that you can take in that sort of setting. And so this is from Minotaur exploration. So Glenn Little, they developed an exploration philosophy in this area that was basically to say, let's focus on the areas where nobody else would have looked before because they're magnetically really boring. So their primary targeting method was to say, if it really sucks in the magnetics, let's pick it up and try some other method to see if we can detect mineralization. So what we're looking at on the right here is an EM survey that they did. They did a whole series of sort of semi-regional EM surveys, and the EM surveys in that not magnetically absolutely dead, but magnetically boring area actually turned up quite an extensive zone of relatively high-grade mineralization that's continuing to grow. And I guess the message there is that sometimes regional surveys can continue to be useful, but you have to consider the focus and psychology of the previous exploration in order to come up with new ways to focus your area selection. And I want to talk a little bit in the time I've got remaining just about another sort of regional exploration, a regional interpretation exercise we did, and I'll try and go through this quite quickly. We did a project with the state government called the Deep Mining Queensland project that looked at the Cloncurry belt, trying to pull apart the 2D and 3D geology of that Cloncurry belt and to develop methodologies for targeting undercover and not sure if I've just lost power in here. I hope people can still hear me. And dealing with the third dimension. So we're in an area, the Cannington region. The Cannington region that I just talked about is down in here. You're actually working on, you might be able to see this red area. So it's an area that just borders on Cannington, but includes the Starra region with copper gold mineralization, the Swan, Mount Elliott, and Merlin, Mount Dore deposits, IOCG family deposits, very different, molybdenum mineralization, some gold dominant, some more copper dominant, but it was an area with a lot of varying styles of iron oxide, copper gold styles of mineralization. And again, one of the things that we built on in this area was the fact that we've transitioned from 200 meter space data, which was the bee's knees 25 years ago, down to 30 to 50 meter space data, which you can see from these two images, gives an enormous amount more detail in terms of understanding structures. So of course, it doesn't really tell you anything more if you're just looking for mag anomalies. But this is an area where the IOCG deposits are not all magnetic targets. So, as I mentioned before, one of the key components to getting this sort of thing right is to actually build up or to have some sort of understanding, to look for an understanding of the time-space evolution of the rock units and structures in that region. And I'm not going to go through them here other than to, and that's not working. I'm not going to go through them here now, but there was an animation that doesn't seem to be working that goes through all of them, but basically shows at the end it's again a very complicated and long structural evolution that culminates in a very young sequence of granites that you can see in through here, the Williams-Naraku sweet granites that are temporally associated with a lot of the iron oxide copper gold mineralization in the region. So the first thing we did here was to do a solid geology interpretation using all the data, geochronology, and everything that was available, build a whole series of sections on a relatively tight spacing in order to build that time-space model, built 3D surfaces from those sections, and you notice in those sections there are large areas of granite. And you can see in this diagram that there are that the interpreted granite edges, which are the edges of these bodies here, correlate with mineral occurrences. And even when you look at granite outcrops that I'm showing over here, relative to an apparent density diagram, you can see that the subsurface distribution of granite is much greater than what you see at the surface. So mapping that subsurface geometry is very important. In this case, what we did was we didn't just do an inversion because you get a, we all know that if you do an unconstrained inversion, you get a bunch of blobs that don't agree with the geology. So what we did in here was a geologically constrained inversion. So what we did was try to produce an interpretation that was consistent with geological observations, but also was made then to be consistent with the gravity and magnetic observations. And what you end up with here is you see these quite extensive bodies of young mineralization associated granite. And then developed models of target types, and I'm running out of time now, but just suffice it to say, we identified 3 different target types that had variants on the juxtaposition of brittle silicates and more ductile, reducing metasedimentary sequences distributed around granite edges. And then we developed an approach where we buffered those various different structures in 3 dimensions, including the right sort of structural juxtapositions and the granite edges, to produce a target map that actually extended into the 3rd dimension, where we could see that these yellow dots here are existing mineralization. The hotter areas there are the ones where all those criteria are met and are relatively proximal to granite. So this is extending into a reasonable depth, a targetable depth. What we combined that with then was I guess interpretations around, well, if you're actually looking for a target at 1,000 meters, which is what we have to transition to in this day and age, you really do have to think a lot more about the significance of an intercept and the significance of the sort of grade that you're getting. So, sometimes we get really focused on grade, where we say, well, if I drill a 1,000-meter target, it better be 4%. But what this is showing is that's very dependent on what sort of mining method you're going to end up with. So if you've got a narrow tabular body that's going to be mined by sub-level stoping, then 4% is not good enough at 1,000 meters. On the other hand, if you've got a big fat body that's disseminated mineralization, even if it's less than 1%, if you've got a 400 or 500 meter intercept and it looks like it might be mineable by a block cave, and if you get that intercept it doesn't much matter whether you get that intercept at 500 meters depth or at 1,000 meters depth or really 1,500 meters depth, with the only constraint there being temperature, rock properties, stress, and that sort of thing. So you've got, you have to change the way you think about and rank targets in that sort of setting. And so we developed a prospective evaluation tool to take that into account when you're considering the value of different prospects. And as I'm using up my time here, I'm going to go through that. I'm not going to go through that in too much detail. There's a summary of everything that I just showed you. I'm going to pass on to the conclusions and say that, really what we wanted to show was that, I think I'm sure this audience would all agree that, more and more exploration expenditure moving into covered regions. And so we're going to be more reliant on adding as much value as we can to regional geophysical data sets. So I tried to show you 2 examples where we've tried to do that, precisely to add that sort of value. And of course, the way you do that is by not treating a geophysical interpretation as give me the mag, give me whatever scraps of geology you got, and I'll put some lines on it. It's integrating all of the field data that you have, all of the geoscientific understanding. It's got to be done by by it's got to involve geologists who have knowledge of the sort of models in terms of morphology and structure that you're thinking of. I think the other thing that I tried to show from Mount Isa was the evolution of geophysically driven discovery that's evolved over time and understanding through better geophysical or through better survey resolution, better understanding of what target you're after, through better conceptual targeting, and even through thinking about how people have approached exploration in the past and trying contrarian options. And I'm sure that it's not the first time that sort of thing's been mentioned today. But the key challenge in all of this, and I didn't really develop this, is that when Pete and I were talking to Ken about participation in this forum, I think 5 or 6 months ago, one thing that we all agreed on is that you do this sort of exercise, and unless you're very careful, or unless you consciously and deliberately set out to make your interpretation and the work that you're doing relevant to explorers, reports and data sets and everything arrive with people, and then they get busy and they just go to the map cupboard or the old backed up hard disk and never get used. So a real challenge in going forward is to make these sorts of more complex interpretations relevant to explorers and put them into a form that explorers can make use of. So thanks very much for the opportunity. Sorry I couldn't be there. That's me done.